Okay, guys, as promised, I'm going to go over a few practice questions with you from Unit 3. And this comes from the Part 1 with intermolecular forces. There is a couple just questions from before, just to keep you on your toes. But I want to just make sure that you understand how intermolecular forces truly work. And this will give you a chance, too, to pause the video, and then you can move on. So let's go ahead. Number 1, which of the procedures outlined below can be used to change the boiling point of pure ammonia? So it's one of those ones where you have to decide if it's going to be Roman numeral 1, 2, or 3, parts of it only, nothing. So pause for just a second. A little pause there. All right, let's take a look at the answer. So Roman numeral 1 says increase the substance's elevation by bringing it to the top of a mountain. I know that sounds like insane, but it totally will change the boiling point of pure ammonia because you're changing the pressure. So number 1 is absolutely yes, that will occur. Oops, there we go. Add more ammonia to the container. This is what we want to think about. It doesn't matter if you have a teaspoon of ammonia or if you have 2 liters of ammonia. Will that change the boiling point of ammonia? And it won't because it's pure. As long as it's pure and you add more ammonia to the container and you're not adding water to it, it's going to be just normal. So that will not affect the boiling temperature whatsoever. And the final thing is increase the pressure on the surface of the liquid. Now, this is considered like vapor pressure, but if you think about this, if vapor pressure is like pushing down basically on the surface of a liquid, then it's going to be harder for molecules to escape that liquid. So that can, in fact, change the boiling temperature. So question 1 is going to be C. Let's look at question 2. The boiling temperature of neon is less than that of krypton. Which of the statements below indicates why this is so? Pause and take a minute. So the statements below, we have, first of all, we just need to think about krypton and neon are both noble gases. So there's not really going to be a lot of electronegativity, if anything. We know noble gases don't even contain electronegativity. So if that's the case, are each of these going to be polar at all? And that is no. So we're not going to have any dipole-dipole. We're not going to have any dipole-dipole. Is there any hydrogen whatsoever? And hydrogen can only be connected to fluorine, oxygen, or nitrogen. So it must be C by process of elimination, but also by krypton is further down on the periodic table than neon is. Therefore, the actual molecule is larger. So they display LDF, intermolecular forces, and that's all. But krypton is more polarizable because the electrons have more space to move. Let's look at the next one. Which of the following statements best describes the changes that take place as CH4, which is methane, evaporates? Pause. Okay, so let's look at these. The covalent bonds between C and H are broken. So let's think about here. First off, do we really refer to these as definitely covalent bonds? Are they polar? I mean, they are covalent bonds, but when they're broken, that means we're talking about the intermolecular forces, and this would be intramolecular forces. So that's not going to be it because part A is talking about intramolecular forces. Hydrogen bonds are broken. There's no hydrogen bonds in CH4. Remember, there's not enough of a polarity, and hydrogen bonds can only occur with fluorine, oxygen, and nitrogen. Attractions due to London dispersion forces are overcome. That sounds reasonable with London dispersion forces. And attractions due to dipole-dipole forces are overcome. Again, we're not going to have dipole-dipole because C and H does not have a high enough polarity or a higher enough difference in negativity, so they're considered to be nonpolar. So our answer is going to be C. The attractions between the London dispersion forces are overcome. Let's look at the next. This one really is not intermolecular forces, but it's a good question just to throw in there to keep you on your toes. How many grams of potassium nitrate with a molar mass is 101 grams per mole, so they took some legwork out for you, are needed to make 250 milliliters of 0.2 molar potassium nitrate. So all we're doing here is making a solution. So take a minute. Okay, let's see what we've got here. We're going to use our good old molarity equation. Molarity equals moles over liters. So we know our molarity is 0.20 moles. And we have to put it in liters. So we take 250 milliliters to liters, and we're going to move our decimal. So we'll have 0.250 liters. And we're going to calculate our moles. So if we calculate our moles, we're just going to multiply 0.25 times 0.20, and we're going to get, my pen here, 0.05 moles. But our question is how many grams? So we need to then convert to grams, and they give us the molar mass. So for every 1 mole of potassium nitrate, we have 101 grams of potassium nitrate. A lot of times, AP questions will give you the molar mass just to save you a minute because they're not worried. They're like, if you made it this far, you know how to find a molar mass. So they just give that to you to just save time. So our answer then is 5.1 grams. So we would add 5.1 grams of potassium nitrate into 250 milliliters of solution, and that's how we would make a 0.2 molar solution. And let's look at the final one. Which of the following compounds has the greatest solubility in water? Remember, solubility is the ability to dissolve. So take a minute. All right. Whoops. So we want to look at the forces here. I'm sorry, guys. We want to look at the forces. So we need to figure out here, we have London dispersion forces only with A. We do have hydrogen bonding with B, C, and D. However, we do have D is quite a bit smaller than A, even being just London dispersion forces. And because that oxygen's on one end of it, it's not going to be, if it were on both ends, it would be a much stronger hydrogen bonding. But this is one case where London dispersion forces are going to overpower hydrogen bonding. So the greatest solubility in water is going to be D because it's going to break down the best. So D is your answer, and it's because this one's going to break apart in the best way. It's less forces compared to the hydrogen bonding here, along with London dispersion, hydrogen bonding here, along with London dispersion, and straight up London dispersion. All right, guys, hope this helps, and I'll keep doing this as long as it helps you. Take care. Bye-bye.